Hello guys, welcome back to my channel Gamma Digamma. So in this video, I would actually like to do that one thing for which I needed the previous two videos to build upon. I'm going to derive the functional equation of the Riemann Zeta function. So as always, let's get started. Okay, so before starting, just one word of advice. Please watch the previous two videos so that you can have a clear chain of thought. Okay, so although this video is all about the Riemann Zeta function, ironically, we're going to start this derivation using the gamma of s in its integral form. So e to the negative t to the s minus 1 dt. Now just instead of s, I want to have s over 2. So integral from 0 to infinity of e to the negative t to the s over 2 minus 1 dt. Fair enough. Now you might not see this coming, but let t equal pi n squared x, and I'll explain in a minute why I'm doing this substitution when there was no need actually. We have integral from 0 to infinity e to the negative pi n squared x, and we have pi n squared x raised to the s over 2 minus 1 power, and dt will just invariably be pi n squared dx. Fair enough. Now what I'm going to do is I'm going to take out the constant terms. So we have this pi to the s over 2 minus 1 and a pi, which will give us a pi to the s over 2, and we have this n squared to the s over 2 minus 1 times n squared. So n squared to the s over 2 will just be n to the s, and we still have integral from 0 to infinity of e to the negative pi n squared x to the s over 2 minus 1 dx. All the other terms that did not have x, I have taken out successfully after applying the properties of exponents and stuff. This is still gamma of s over 2. Now what I'm going to do is I'm going to take all these other constant terms on the left hand side. So this pi now will have a negative power on left hand side, gamma of s over 2, divided by this n to the s power, and that is still equal to integral from 0 to infinity e to the negative pi n squared x to the s over 2 minus 1 dx. Now what I'm going to do is I'm going to make a sum run from n equals 1 to infinity on both sides naturally. I can do that because both these guys are convergent. So now again, by uniform and absolute convergence, interchange these two. Over here we have pi to the negative s over 2, gamma of s over 2, and the sum from n equals 1 to infinity of 1 over n to the s being equal to integral from 0 to infinity x to the s over 2 minus 1 sum from n equals 1 to infinity of e to the negative pi n squared x dx. Now on the left hand side, notice what this guy is. It's the Riemann Zeta of s by the infinite sum definition. being equal to, well, this actually looks familiar, doesn't it? It does remind us of yesterday's Jacobi theta function. So the Jacobi theta of x was the sum from n equals negative infinity to positive infinity of e to the negative pi n squared x. Now the problem is this sum is going from n equals 1 to infinity, but we can exploit the fact that this is going to be even. So sum from n equals negative infinity to minus 1 of e to the negative pi n squared x plus, you know, the time where n is 0, so e to the 0 is 1, plus sum from n equals 1 to infinity e to the negative pi n squared x. All I've done is just split this from negative infinity to negative 1, then the 0 term, and then 1 to infinity. Now because we have an n squared, any negative stuff you put in will just get squared and will have a positive value. So that means this guy is actually same as this guy. So we can write this as 1 plus 2 times the sum from n equals 1 to infinity of e to the negative pi n squared x. And that's Jacobi theta of x. Now what I'm going to do, just for some convenience, I'm going to call this guy, this sum, psi of x. So psi of x is the sum from n equals 1 to infinity e to the negative pi n squared x. So that means the Jacobi theta of x is just 1 plus 2 times psi of x. Now this psi, I would like to point out just at the start, is not the digamma or any polygamma function. It's just a fresh quantity, it's a fresh variable. And in this integral over here, it turns out we just have psi of x. Dx. Fair enough. Now what are we going to do? Good question. Good question. So now what I'm going to do is I'm just going to take this left hand side as it is. So pi to the negative s over 2 gamma of s over 2 zeta of s is equal to, well, the integral from 0 to infinity I can split on the interval as integral from 0 to 1 of the same argument plus integral from 1 to infinity of the same argument by the linearity. Obviously I'm doing this. So now what I'm going to do is I'm going to call this first guy I1, and we're going to actually evaluate that on a fresh page. So see you there. Okay, this is indeed I1 as discussed. I'm going to make a nice substitution. Let x equal 1 over t. So when I do that, I'll have infinity here and 1 here. Then we have 1 over t s over 2 minus 1 psi of 1 over t and the dt. So dx is negative dt over t squared, so negative divided by t squared. Now if I do some simple algebra, take the negative, correct the order of the upper and lower bounds, do some algebra on the free t's over here, t to the negative s over 2 minus 1 gamma psi of 1 over t dt. Now psi was actually related to the Jacobi theta, and if you remember the functional equation of the Jacobi theta, Jacobi theta of x was 1 over square root of x times the Jacobi theta of 1 over x But Jacobi theta, if you remember what I did on the previous page, can be expressed 1 plus 2 times psi of x. And I can do that on all sides. 1 plus 2 times psi of 1 over x this time because of the argument change. So on rearrangement, I have psi of 1 over x is equal to square root of x over 2 plus square root of x times psi of x minus half. And this is exactly what I'm going to plug in for I1 here. So I1 now becomes, I can split this into three integrals. Integral from 1 to infinity, take the half outside. Instead of x we have a t. Square root of t is t to the half. Multiplied with this guy is basically adding power. So minus s over 2 minus 1. And well, that's this first part. I'll put a dt there, plus the second guy, there's no half now, integral from 1 to infinity, t to the half minus s over 2 minus 1, psi of t dt, and finally negative 1/2 integral from 1 to infinity, then just this t without anything, so t to the negative s over 2 minus 1 dt. Let's just check that. Yes, that's right. So let's evaluate these guys separately. So the first one can actually, the power can be simplified a little bit, I believe. T to the negative s over 2 minus half dt plus integral from 1 to infinity t the minus s over 2 minus half psi of t dt minus half integral from 1 to infinity t to the minus s over 2 minus 1 dt. We can do the first thing properly. The antiderivative is going to be easy, just use the power rule. T to the negative s over 2 plus half divided by the new power, which is minus s over 2 plus half, evaluated from 1 to infinity, plus keep this integral with the psi as it is, and then evaluate this guy. So minus half t to the negative s over 2 divided by negative s over 2 evaluated from 1 to infinity. So now an exponential function, or let's say algebraic, not exponential but algebraic function with a negative power at infinity will certainly go to 0, and at 1 we have a 1, so take a negative half and we can factorize out the 2, so 2 over 1 minus s, like that. Keep the middle integral as it is, we'll need it a little later. And then a similar approach for this, at infinity we'll have a 0, and then eventually we'll have plus half and negative 2 over s, like that. So the 2's will cancel out. We have negative 1 over 1 minus s minus 1 over s plus this dangerous integral over here. I can do some simplifications making I1. Now I'm going to change the variable from t to x because it's a definite integral. I can do that, and on associated with this we have 1 over s times 1 minus s. I just cross multiplied into a common denominator here. Fair enough. Nothing that was too great or something. It's time to plug I1 back into our general expression. So basically we had pi to the negative s over 2 gamma of s over 2 zeta of s is actually equal to integral from 1 to infinity x to the s over 2 minus 1 psi of x dx, and then the I1 expression, which was integral from 1 to infinity x to the negative s over 2 minus half psi of x dx minus 1 over s times 1 minus s. Now just simplify a little bit, clean it up a little bit. We can take these integrals to have a common psi. So x to the negative s over 2 minus half plus x to the s over 2 minus 1, which have a common factor of psi of x dx minus 1 over s times 1 minus s. Now this integral over here, I was actually requested this integral over here, this crazy integral over here, where psi of x is actually related to the Jacobi theta function. But the thing is, this is almost impossible to solve, because even if you were to break this into its sum definition again, you would have to deal with incomplete gamma functions, because the interval of integration is from 1 to infinity, not from 0 to infinity. So incomplete gamma functions, and I don't believe this has an elementary antiderivative. I mean, you'd have to probably use hypergeometric functions eventually or something, or incomplete gamma or special functions. So, but now the trick here is to not evaluate this, use symmetry. Because if you transform s to 1 minus s on basically both sides, you'll have pi to the negative 1 minus s over 2 gamma of 1 minus s over 2 Riemann Zeta of 1 minus s being actually equal to integral from 1 to infinity x to the minus 1 minus s over 2 minus half plus x the 1 minus s over 2 minus 1 psi x dx minus 1 over 1 minus s and s. And if you simplify the right hand side a little bit, integral from 1 to infinity, this guy will just become x to the s over 2 minus 1 plus x to the minus s over 2 minus half psi x dx minus 1 over s times 1 minus s. So it doesn't change even if you change s to 1 minus s. This right hand side doesn't change at all. So this right hand side is equal to pi to the negative 1 minus s over 2 gamma of 1 minus s over 2 zeta of 1 minus s. And what did we originally start with? Pi to the negative s over 2 gamma of s over 2 Riemann Zeta of s. So this invariance under changing the argument from s to 1 over s, this relation is captured in what we call the functional equation for the Riemann Zeta function. It's just a beautiful result, really nice result. Okay, and this result is particularly useful because it allows us to perform analytic continuation practices on the Riemann Zeta function. So although the Riemann Zeta is not defined in the conventional sense for negative integers, negative arguments, we can still extend it using this analytic continuation, using the functional equation of the Riemann Zeta. Now before I forget, this substitution, if I wasn't clear, using pi times n squared x was useful because we had this e to the negative pi n squared x, which was basically building towards the Jacobi theta function, because the Jacobi theta by default has this e to the negative pi n squared x. So this substitution was actually helping us build towards the Jacobi theta function, and that's what actually we employed most of the time in this proof. Okay, so please like, share and subscribe to my channel, guys. Recommend me to your friends, spread the word of Gamma Digamma in the math community. And although I briefly told you that the functional equation is used in analytic continuation of the Riemann Zeta function, I will most probably make a video explaining with a little depth that basically how that works, and we will probably derive a more compact form of the functional equation in that video. So stay tuned for that, guys. In the meantime, stay home, stay safe, keep doing math. Peace out. Signing off.